Okay, everyone. Assalamualaikum warahmatullahi wabarakatuh. So, in this time, I want to present my research entitled Behavior of Code Steel Back-to-Back Channel Build-Up Sections Under Bendings. And this research is conducted by me, Ridho Fitrah, and Anissa Pritamelinda as my co-partner. And I come from Civil Engineering Department, Universitas Darmandalas, and Anissa Pritamelinda come from Civil Engineering Department, Engineering Faculty in Universitas Negeri Padang. So this research was started by thinking about how we see that the cold form steel has been developed into something bigger. I mean, when the cold form steel can be used in many kind of structures, included long span structures. And we can see that in Indonesia, especially in the Padang city, cold form steel is used as the for the roof truss in the residential house, and there is a development where the cold form steel will be developed into a long span structures, and obviously that it can be used as the to resist a larger load. So for that things to resist the larger load and for the long span structures, the build-up section can be an options. So build-up section of cold form steel are commonly used to uplift its capacity in torsional compressions and tensions. And there is a research that the build-up section is not really new. There are so many research has been revealed in terms of the build-up sections capacity and doing such kind of experimental and numerical analysis. So compared to a single sections, I mean just only one sections of conform steel, the rigidity and the capacity of the build-up sections have been proven increase about 20% until 50%. And one of the sections, build-up sections, is back-to-back channel sections. So the back-to-back channel section is there are the when the wave is connected by using a self tapping screws, and the wave and we know that the back-to-back was assembled by is assembled by connecting the waves and use and we use the self tapping screw to connect it. So, however, there is an issues concerning the build-up back-to-back channel sections when they are designed as a flexural member. So we always knew that when the core form steel is used as a roof truss, it means that in the basic concept, you just only experience about the axial as the axial members. So when we want to use the back-to-back channel sections as a flexural member, there is an issue concerning build-up back-to-back channel sections. So most of the cold form steel sections which are subjected to bendings, so experience local and lateral torsional buckling. So these bucklings dominantly happened due to the beam span and web depth to plank width ratio. So this study is focused to investigate the flexural capacity and the failure that's shown along the beam specimens by doing experimental in three-point bending scheme. So the results of the specimen with several thicknesses which are commercially used, and you know that in the roof trusses we always use a commercial product like Smart Trust and Tasso. So I want to know about there are several thicknesses that they product that they are produced, but they product in so many kind of various thicknesses like Tasso and Smart Trust. So several techniques which are used commercially used as the common structures in residential building are shown and discussed. Okay. So this is the methodology. As I mentioned before that the 3-point bending scheme is used in this research, and I was using UTM in the Universitas Negeri Padang, and this specimen has a length about 65 centimeters. So the experiment is conducted by testing 9 specimens of back-to-back channel sections which have various thicknesses. So each section has 3 specimens. So because I already stated that I use the various thicknesses to see the variable of thicknesses. So generally, the conform steel profiles used in this test are single sections. So it is, as I mentioned before, that uh, these cold form steel are commonly used and commercially used in the residential building area. So there is 3 sections where C75 75, C75 80, C75 100, and each of them obviously has the thicknesses. So C75 75 has thickness 1.75 millimeters. C75 80 has a thickness about uh, 0.8 millimeters, and C75 100 has thickness about 1 millimeter. So this is I show to you specifically about 9 specimens where the BGR 1 and 65, taking the example, is represent about the specimens and the number of tested, and the number and the last number 65 is represent the thickness. So there is a leaf, flank, web thickness, and web thickness, and as you can see in this video. So because of back-to-back sections, I think the web thickness, when I given a sign of star in here in there, when it's 0.65, when we connect it to back-to-back section, it is obviously shown that the web thickness it must be increased doubled. So after I conduct 3-point bending scheme and I obtain data about the flexural capacity each of them. Oh, I'm sorry, not flexural capacity, but load and deflections. Load and deflections. Load and deflections curve that that automatically generate from the UTM. So as you can see that in this graph, the 9 specimens have been shown about the load and deflections, and you know that there is a BGR blah 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 and 9 specimen that we know that this is a very typical graph, but especially each specimen has slightly different stiffness for every thickness. So BGR 100 specimens have the highest load capacity. So the average experimental moment capacity for specimen BGR 100 is higher than BGR 65 and BGR 75, about 21.9% and 10.7%. And most of them has a failure mode, local buckling and lateral. So we specifically see that what is the local buckling. So local buckling in this specimen uh, experience in the compression flank. So the compression flank generate the local buckling, and it means that there is a point, the yielding point has been reached. And however, the local buckling exactly happen when the inelastic zone is reached. So it can be stated that thickness in each specimen contribute to increase the rigidity in the compression flank before local buckling is. And we know that the lateral torsional buckling is the common phenomenon that happens in the column steel due to the thin web. As you can see in this figure, that the lateral torsional buckling failure generated along the span. It also confirms that all specimens have the similar patterns in terms of lateral deflections and twisting in the anti-clockwise. So I concerned about the local buckling and the lateral torsional buckling. As you can see that this is the final step, and you can see, as you can see in this figure, that the specimen twisting anti-clockwise both of side, and it caused so many failure in terms of the sections and along the span. So, but I think that increasing thickness, so the thickness having, even though that they are having a specific, they are shown a similar pattern of the failure, but I think it depends. The thicknesses, whether at web or the compression flank, apparently leads higher torsional rigidity, and it may cause the reduce the angle of twist. So the angle of twist of nine specimen is very different. Often twist before it continues, increasing the deflections after ultimate load capacity is. So the conclusion of the research, this research aimed to comprehend the bending behavior of column steel, back-to-back build-up sections with the various web thicknesses. And based on the experimental result, I can conclude the 3 points in as shown. Increasing web thickness in column steel of back-to-back build-up sections will increase the moment capacity about 10% until 20%. Then the observed failures for all specimens are local buckling and lateral torsional buckling. So we can see that effects of the web thickness in all specimens are increasing the stiffness, compression flank, and torsional rigidity. Both compression flank and torsional rigidity, as long as local buckling and lateral torsional buckling is generated along sections and span. So this is a very start research for me, and I hope that I can continue to advance this research. And I hope that there is a discussions about my research, and hoping that to make it perfect. Thank you very much for your attention, and assalamualaikum warahmatullahi wabarakatuh.